All right. So if we solve this system by substitution, it says check your answers by graphing. So the graph on this one's going to be a little bit funky for graphing, just because we have an x squared plus a y squared. Anytime you have an x squared plus y squared, that will end up creating a circle on a graph because it's not quadratic. Because quadratic means that you've got an x squared, an x, and a regular number. This one does not have an x squared, a regular x, and a regular number. It's got x squared and y squared. We'll deal with that in a little bit. The math on this one, though, is going to be the same as what we did on the previous page with substitution. Because this y is already solved for, it's a linear equation. Because this y is already solved for, we can take the value of y and substitute it directly in to the top equation. So let's do that. So take your value of y, which is negative 3x plus 10, substitute it in for y up here. So we're going to rewrite that first equation as x squared plus, and when you write the negative 3x plus 10 in for y up here, put it in parentheses. So we're going to have negative 3x plus 10 squared equals 10. All right. Any thoughts on what to do next here? What do you think would be probably a good idea at this point? Yeah, we should probably multiply this out because we have an x squared outside of the parentheses already. If it was just like a regular number, we might be able to get away with like vertex form here, but there's already an x squared out here. So we should probably multiply it out and combine our like terms and then kind of deal with it from there. So if we're using FOIL, I'm just going to write it out just to show you exactly what's happening here. This would be negative 3x plus 10 times another negative 3x plus 10. And then that equals 10. So we're going to have to use FOIL here. So we're going to have to do first outer, inner, last, and then combine our like terms. So that'll be x squared. Negative 3x times negative 3x will be plus 9x squared. The outer terms would be minus 30x. The inner terms would also be another minus 30x. And then last times last, 10 times 10 would equal 100. And then the whole thing is equal to 10. We use FOIL. Put the two terms in the middle together. That'll be minus 60x. And I'm also going to go ahead and just subtract the 10 from both sides in this next step as well to make that 90, because we need the whole thing equal to 0 in order to solve for x. So that'll give us, I'm also going to add the x squared and the 9x squared. So a few things are going to happen between this line and the next one. So x squared plus 9x squared is 10x squared. Negative 30x minus 30x would be minus 60x. And then over here, we can subtract 10 from both sides, so that'll be plus 90 equals 0. Now, we might end up just using the quadratic formula, but before we do that, everything here is divisible by what? Was it? 10, yeah. So let's just go ahead and divide everything on both sides by 10, just to reduce the size of the values here. So that'll be x squared minus 6x plus 9 equals 0. Oh, that's convenient. That's factorable. So we could use the quadratic formula, but this is also factorable. What two numbers multiply to positive 9 and add to negative 6? Negative 3 and negative 3, yeah. So that'll be x minus 3 squared, because x minus 3 times x minus 3 x minus 3 squared equals 0. And then square root both sides to get rid of the squared here. This is a perfect square trinomial, so we get a square of a binomial. We could have written x minus 3 times x minus 3 and as two separate sets of parentheses. But because it's the exact same set of parentheses twice, we're only going to end up with one answer here. So that'll be, just going to go up over here now. So that'll be x minus 3 equals 0. Add 3 to both sides, and x is equal to 3. All right. So this one has one solution. So if we're thinking about what this might look like, just in general, I'm going to pause here for a second. I'm going to turn back to our second page from yesterday. If you look at the examples of circles and lines, it's going to look something like this. So that. If x equals 3, let's figure out the y value. It's going to be easier to figure out y if we plug it into the second original equation, because y was already solved for. So that'll be y is equal to negative 3 times the value of x, which is 3, and then plus 10. So that would be 1. Negative 3 times 3 is negative 9. Negative 9 plus 10 is 1, so y equals 1. So the answer, the point of intersection of that line and that circle is 3, 1. Now, in terms of showing this on a graph, we're actually going to have to write in 3 equations on our calculators to make this work, because as far as I know anyway, these calculators do not have an option for a y squared. It's just an option for a y, which means we're gonna have to do a little bit of math to make this work. So off to the side here over on the left, we want to get y by itself if we want to actually enter anything onto the graph on the calculator. It has to work that way. So if we were to go over here, I'm just going to write x squared plus y squared equals 10. If we're solving for y, we first have to get rid of the x squared, right? Subtract x squared from both sides. We good with that? Okay. So that'll be y squared equals negative x squared plus 10. And then what would we have to do, or the opposite of x squared plus 10? What would we have to do to get y by itself? Square root it. So what ends up happening here is we'd square root y squared, and we'd square root the opposite of x squared plus 10. By the way, this is not square rooting a negative number. This is square rooting the opposite of whatever x is. Maybe it's negative, maybe it's not, but it's not exclusively a negative number, so we will not have the imaginary unit here, so we don't need to worry about that, because we don't know what x is. If x is a negative number, then the opposite of that would turn that into a positive number. So we are not treating this x squared as a negative number with an imaginary unit. I just want to make sure everybody's okay with that. So when we do this, we're going to get y equals plus or minus the square root of the opposite of x squared plus 10. And the reason why we need to write this as 2 separate equations is because one of them will be the positive, the principal root, and the other will be the negative root. So the 2 equations that we're going to write are y equals the square root of the opposite of x squared plus 10, and y equals the opposite of the square root of the opposite of x squared plus 10. So those are the 2 different equations, because the plus minus means we have the plus version and the minus version, or the positive version and the negative version. So if we type both of those in, that should give us our circle. And then if we type in the y equals negative 3x plus 10, that'll give us that line. And then hopefully we'll be able to see that these things end up working. So what I'm going to do real quick is in here, I'm going to use y1 and y2 for the top and the bottom of my circle. But I also want to make the circle the same color. So I'm just going to scroll to the left and hover over the red here. And I'm going to change red to blue. A lot of colors here. Here's blue. Okay. And then click OK, because I want it to look like one graph. So I want to make sure my colors are the same there. So here we go. Y1 will be equal to the square root of the opposite of x squared plus 10. And then here we've got negative, or the opposite of the square root of opposite of x squared plus 10. Now here, I'm not going to type in the third one yet because I don't want to show you the line just yet. I want you to go ahead and hit graph once you have those typed in, just to see what it ends up looking like. It should be a circle right around the middle of your graph. I need to change my window here. I'm going to change my zoom. I'm going to go back to standard. There we go. And it doesn't really look like a circle because the scale along my x-axis and y-axis are a little bit different. So if you want to change it to actually make it look more like a circle, if you click the zoom button and you click on option number 5, z square, that will even out the x and the y-axis right there. Now, I'm not exactly sure. I'm going to zoom in right in the middle. I'm not exactly sure why these don't necessarily. I'm guessing it has to do with some of the numbers that are involved and not involved here. But in terms of the numbers that you could actually connect here, so there are some missing values that should be on there with our graph. But you can see it looks like a circle. There's some gaps there, but that's not really super relevant to what we're doing. So now we have our circle. Let's go ahead and head back out to our y equals menu, scroll down, and I'm going to go with magenta or pink for this next one, just because I think that contrast would be a little bit easier to see. So we're going to have negative 3x plus 10. And if we go back, we said that our intersection point is the 0.31. So that should show up if I go back to the graph. And there it is, right there over on the side. So that line basically glances off that circle coming down over there. If we go back to zoom and I square this out again, z squared or z square. Oh, I need to zoom out actually in order to make that happen. There we go. There it goes, right there. So that's what it looks like. We basically just verified that, yeah, this does in fact match with what we have going on. So to graph a circle on these calculators, you basically have to use the positive and the negative square root of the right side of the equation once you get y by itself. Just because, as far as I know, like I said, as far as I know, these calculators don't do, they don't do y squared. However, I think Desmos does. So like if you went to Desmos and you typed in x squared plus y squared equals 10, that probably will just go ahead and show that graph. In fact, I'm just going to open this up. Open up Desmos on my phone real quick and see what we got. All right, so here's our graphing calculator. And if we say x squared plus y squared equals 10. Yeah, there it is. So Desmos is a little bit better. Go away. Okay. All right. So it's a little bit, honestly, it's a little bit easier on Desmos just because you don't have to solve for y. It just understands what you're doing. And then we can graph the other one. We can say y is equal to negative 3x plus 10, and there it is. So same thing. We'll look at them side by side. It's the same two graphs. However, the little invisible parts on the calculator are actually filled in on Desmos. So either way, looks the same. All right, let's take a look at this last one. So this last one says solving quadratic equations by graphing. All right. Now, what do you think is going on here? Any thoughts on this one? Like, this doesn't look like anything we've seen before, does it? Looks kind of nutty. In fact, now that I have Desmos open, I'm just going to go ahead and type this entire equation into Desmos just to see what it looks like. And then from there, I'll show you how to solve it. You would not necessarily be able to type this into the calculator just because it doesn't like it if you don't have a y equals, it doesn't like it for graphing. So if we type in, let's see, 3x squared plus 5x. The only annoying thing about using Desmos on a phone is that the buttons are very small. And that's going to equal the opposite of x squared plus 2x plus 1. So this graph here, it's kind of weird, huh? Almost looks like parallel lines. But the thing we need to pay attention to here is, let's see, way out. Hang on a second. Let's get back to the middle. All right. So those appear to be parallel lines, don't they? Do parallel lines intersect? No. So just in terms of the visual here, I'm thinking we'll probably end up with no real solution. So Got an Instagram message. So check that later. On these problems here, when we're dealing with two things, by the way, each side of this looks like a what? What does that look like here by itself, the left side? Like just the left side, what would we call that if this is all that it was? That'd be quadratic, right? Yeah, standard form of a quadratic. What about the right side? Same, right? Standard form of quadratic. And the thing is, those two things are equal to each other, aren't they? I mean, it literally tells us they are. So what we could do and what we're going to do is this. We're going to say, we're just going to set each of these things equal to y. And the reason for that is they're already equal to each other. And so if they're equal to each other, they would also be equal to something that is the same between them, which would be y, which would allow us to graph them separately as two different parabolas, just to see if those parabolas do in fact intersect. So we're going to say y equals 3x squared plus 5x minus 1. And then we're going to graph that. We're going to check it with our calculator, but we're actually going to use what we know about graphing in standard form. So we're going to do this by hand, and then we're going to double check on our calculator. So if I want to figure out my axis of symmetry here, what do I have to do? This is just a review of what we're doing for graphing a parabola. What's our first step for graphing a parabola from standard form? There's a little formula to figure out the axis of symmetry. It says x equals, what's that? Yeah, opposite of b over 2a. That is our axis of symmetry right there. And so what we're going to use is the opposite of b. Opposite of 5 would be -5. Over 2 times a would be 2 times 3, which would be 6. So our axis of symmetry is at -5/6. I'm going to use a pencil for this. -5/6 is like 0.8-ish. So -0.8 is almost at -1. This will be a bit of an estimate for this axis of symmetry because we don't have that exact value on this graph, but we can go and put a little dotted line there. And that's fine. And then to figure out the y value of our axis of symmetry, we actually need to go ahead and, well, we don't need to, but it's probably going to be a little bit faster to use our calculators for this part. So heading on back here, use the equation. So 3 and then parentheses, -5/6 squared plus 5 times -5/6 minus 1 is -37/12. Now, that's not super helpful for me. I know that's going to be like -3-ish. Actually, it's going to be just a little bit less than -3. It's like -3 and 1/12, I think. But if we go here and we change our fraction to a decimal, yeah, -3.0-ish. So it's basically -3. So we can go down on this line here to -3 and like just beneath that line, put a little dot. So there's our vertex. So the vertex is -5/6, and we'll just call it -3.1-ish. For practical purposes on our graph, that's going to be pretty good. Now this one definitely faces in an upward direction because the value of a is positive. We know that. Where's our y-intercept at? Was that -1? Yeah, because the value of c is the y-intercept, so -1. We need to get a few other points on here, so I'm just going to go back and type in a few more. So I'm going to copy and paste my function. I'm going to delete these fractions. We don't want the fractions anymore because we're just going to use whole numbers to fill the rest of this out. So let's go with +1. Let's just type in 1. And that'll give us 7. So the point, 1, 7. So over 1, up 7. Well, we don't have that. That's not going to fit on our graph. How about -1 then? -1 would be -3. Thanks. Now, these are not necessarily going to be even because we don't have a whole number for our vertex. And so the points that we get are going to be hard to reflect. So that's why we're kind of doing this a little bit differently here. So 2, -2, -2, -2, 1. That's up here. All right. So let's see. We got 4 points there. It's a little bit odd looking, but it's going to be pretty steep. -3 is not going to work. +1 was up at 7, so that's going to be up here kind of far. So let's see. How far away is this? This is about 1.2. So if we go 1 and then 0.2, maybe about here. I'm just going to guess at this point, just because, again, these numbers are going to be a little bit imprecise based on the fact that our vertex is going to be very hard to reflect across, but our graph itself is going to look something like that for that parabola there. Now, the other one should be a little bit easier to figure out. Because this one's going to say y is equal to the opposite of x squared plus 2x plus 1, meaning that our axis of symmetry is going to be a nice whole number. Because if we say x is equal to the opposite of b over 2a, that would be -2. A is -1. -1 times 2 is -2, so that equals 1. So our vertex on this one is at 1. At least the x value of it. So our axis of symmetry, right there. And if we plug in 1 back into x here, if you square 1, you get 1, then take the opposite of it, that's -1. -1 plus 2 is 1. And then 1 plus 1 is 2. So the vertex on this next one is at 1, 2, which is right here. Which means I need to extend this red line just a little bit further because I know that's going to go all the way up to 7 before it ends up hitting. So if we flip this upside down, this is going to be an upside down parabola. And this is a little bit weird because it looks to me like maybe they will intersect. We'll see. Our y-intercept is at 1, so that is interesting. Curious about that. Maybe my Desmos graph is not a good example to start with. Yeah, the Desmos example is not a good thing to start with. There is an intersection point. So the whole parallel lines thing, that didn't really work very well. These are going to intersect. So let's keep going here. So we end up with, let's see, if here's our y-intercept of +1. So here's 1 here. And we can reflect that across at 2 because we know that we have a nice whole number here for that. And then let's see. Let's just do one more value of x. We can plug in 3 for x. So 3 squared is 9. That would be -9. 9 times 2 is 18. -9 plus 18 is 9. And then 9 plus 1, no, that doesn't work. So, no, we're using 3. Sorry, 2 times 3 is 6. -9 plus 6 would be -3. -3 plus 1 is -2. So -2 right here. And then 3 -2 right here. Okay. So this one ends up looking about like this. So we actually have 2 points of intersection here. Now, I'm not exactly sure why they wanted us to solve this one by graphing necessarily, just because solving by graphing here, these are definitely not nice whole values from where the points of intersection are. And most of these are going to be estimates anyway. So I'm trying to think of the best way to do this. Let's go ahead and use our calculators. And this is a perfect example of why I always say that graphing is not usually a good way to solve something. I would have absolutely recommended solving using the quadratic formula or factoring and then going back and showing the graph, but like verifying your answer with the graph as opposed to solving by graphing. But that's the way this one was set up. So let's go ahead and put both of these in on our graph here. So we're gonna have 3x squared plus 5x minus 1. And then I'm going to change this one back to red, just so they look a little different. And that was the opposite of x squared plus 2x and oops, plus 2x plus 1. All right. And if we go to the graph, hopefully these will look relatively similar to what we got going on here. The colors are inverted from what we have on our, what I have over here on the graph, but those are looking pretty good in terms of how these turned out. Red, blue, blue, red, I should have inverted those. All right, so I'm going to zoom in a little bit just to get a bigger picture of what's going on here, make it look a little bit more like what we have on our graph here. We should still be able to see both points of intersection if we zoom in a little bit. And we got the top one, but not the bottom one. That's okay. Let's navigate to the top one first and figure out that point of intersection, because these calculators will give us the intersection points. So what you want to do now is hit the second button, so hit the blue button, and then go over to where it says trace, hit the button that says trace, and it'll open up a calculation menu. We saw this yesterday a little bit. Head down to option 5, go to intersect, because we're trying to figure out where the two lines intersect. And then you just get to choose between your two lines. So the first line is here at y1. That would be line y1, 3x squared plus 5x minus 1. Hit enter. And then the next one, it's going to put your graph on the y-intercept. Go ahead and navigate over, hit the over button until you get past the point of intersection. Just because it's going to say, all right, I'm checking between that point down there on this graph and this point up here on this graph. And the intersection point is definitely in between those. So use the arrow over button to move over on the x-axis. So kind of get near where the vertex is. And then if you hit enter, and then it's going to say yes, and then you hit enter again. And it says the intersection is right here. 0.4253905. It's not going to give it to you in simplest radical form. If we solve the Eastman quadratic formula, we would. And then here we've got 1.669824. So let's go. Let's use 3 decimal places here. So one of our points of intersection, and I'm going to draw arrows to these because that's this one here. I'll use black. So this point here is the point 0.425, comma 1.67. That's what, or round 2. That's one of our 2 points of intersection. So that would be the point of intersection of these two. Now, pay close attention to what we're about to do here, because I'm going to bring it all back to the original equation. Because there is going to be a little bit of a difference, because, well, we'll see it when we get there. So I'm going to zoom back out, zoom out, and let's see, I'm going to zoom out here, but then I want to zoom back in, bless you. I'm going to zoom back in over here where the other point of intersection is going to be. So we'll let these graph. Okay, zoom in, and then let's kind of navigate down to where that other point of intersection looks like it is. So we'll go down here, zoom in where we think that point of intersection is going to be, and we'll get our 2 graphs coming down here. We'll be able to see where they intersect. We'll figure out the intersection point on this next one, and then we'll talk about the actual answers for this one. So here's our other intersection point. So we're going to go back to second, calculate. Intersection is option 5. First curve will be that one. Hit enter. Second curve is up there. That looks good to me. They'll say yes. And there we go. That point of intersection to the nearest 3 decimal places is going to be right here, which is negative 1.18 actually, negative 1.18, or 1.175 actually, 1.175. because we're going 3 decimal places, and then negative 2.732. And honestly, we did pretty good with the graph itself, because those look to be about on the actual graph where those numbers are. So it's a decent job of getting the graphing on there, especially without whole number values. Now, this problem actually only has 2 numbers for answers instead of all 4 of them. Does anybody know why? Look at the original equation for me. What's that? Yeah, the original equation doesn't include y. So because the original equation doesn't include y, we're only solving for x here. Does that make sense? We needed to use these equations to look at them to see where they actually intersected. However, this problem here only uses x. So we are only solving for x. So I'm going to just put a little arrow here. See, the original equation only has x. Therefore, we only solve for x. So we are not going to use, we're not going to use the y values in our answer here. So the 1.67 and the negative 2.732, those are not relevant to our answers because the original equation did not have any values of y, so we don't want any values of y in our answer. So the answer is going to be x equals, we'll use braces here, negative 1.175, comma, 0.425. And we're using braces because those are both values of x, and we only want values of x for our answer. Because the original equation did not have y, so we don't need y. All right, any questions on that? So honestly, if I were solving this, I wouldn't use a graph to solve it. I would write my equations like this, and then I would either use elimination or substitution, and just go from there. Actually, I would probably just go back up here and get the thing equal to 0. And then solve for x. That's how I would do that. But it told us to solve by graphing, which is why we went around and did this long way to do it. So if given an option, just get that thing equal to 0 and solve for x, because that's all that needs to happen on this one. So let's go ahead and pause for a moment.